All right, hi everyone. So let me just get this situated here. All right, so for some reason, my computer is not behaving. So we're gonna do this kind of old school. All right, so we're going through a couple examples here. So the first is, so this is all for uniform circular motion. So how fast would a car need to be moving around a circular arc of radius 95 meters for its centripetal acceleration to be 9.8 meters per second squared? All right, so here they're telling us the centripetal acceleration, right? And that actually is a value of 1g, so g being 9.8 meters per second squared. So this problem is asking how fast, all right, so that is speed. All right, so we're solving for the magnitude of velocity, would need to be moved in an arc of radius 95 meters, all right, so we know that's the value of r for radius. If it's moving it at 1g. All right, so the way we could do this, well, we can picture, well, it's moving in a circular arc, right? So arc is literally just a segment of a circle, so we have some sort of circular path here. Perhaps this is our car, right? So if we're drawing its velocity, well, maybe it's moving along the trajectory along this direction, right? So our velocity vector would be tangent, right? So there's a velocity vector. And the acceleration, the centripetal acceleration, would then be pointed towards the center of the circle, or perhaps there is the center. And we know the distance from the center to its location, and that's 95 meters. All right, so we do know that centripetal acceleration is equal to v squared over r. All right, so if we are solving for the speed, we just need to rearrange this and solve for v, because we already know the acceleration and we know the radius. All right, so I'll multiply both sides by r and then take a square root. All right, so that was pretty straightforward. So now you just need to plug and chug. So the square root of our acceleration, 9.8 meters per second squared, multiplied by the radius of the circular path, which is 95 meters. All right, so a lot of times in problems they'll try to trick you and give you the diameter of the circular path, so just be cautious of that. When we do the math here, we end up with the speed being 30.5 meters per second, right? And just to kind of see if this is reasonable, so remember kind of a offhand way we can kind of convert this to miles per hour, roughly speaking, would be doubling this. So the miles per hour would be roughly 61 miles per hour. Actually, if we legitimately converted, it would be 68 miles per hour. So a car would be needing to move at 68 miles per hour to feel an acceleration of this amount. All right. So that type of problem, pretty straightforward. All right, but let's look at an example that's very interesting. All right, so let's see. Let me move this up. Try to see. I kind of have my phone taped in a very interesting way. Okay, so here we have the International Space Station orbiting Earth at an altitude of 360 kilometers per hour above the Earth's surface. So if we're kind of sketching this right off the bat, all right, so perhaps here is Earth, and then we've got an orbit, and we'll discuss orbits more later. But it basically means that the International Space Station is taking a circular path around the Earth. The acceleration required to keep the International Space Station in orbit along the circular path is provided by Earth's gravity. So something to note, the acceleration due to gravity is actually going to gradually decrease with altitude, right? So we usually think, oh, acceleration due to gravity, 9.8 meters per second squared. That is true on the surface of the Earth, or near the surface of the Earth, right? So as we move away from the surface of the Earth, the value of that's going to decrease. And again, we'll talk about more the reasoning how this occurs, and we'll actually derive an equation later on in class to figure out what the value of the acceleration is at a certain location away from whatever planet we're looking at. So in here we could do it for the Earth. But if we were to measure the gravitational acceleration at the location of the ISS, it'd be 8.78 meters per second squared. All right. So first we're to find the orbital speed of the ISS, and then we want to find how long it takes the ISS to complete one orbit. So one thing to note here, this here, how long in minutes does it take? That's a quantity known as period. So just an FYI. All right, so sketching out a diagram, we already have something pretty nicely done here. So maybe I'll draw a dot here. I'll label that as the ISS, and perhaps now this time maybe it's moving in a circular path in the clockwise direction. All right, so that would be its velocity vector. Its acceleration vector would be pointing towards the center of the circle. And here, the center of the circular path here is actually going to be the center of the Earth. Right? So this is why it's important that the problem tells us the radius of the Earth is this much. All right, so part A, what is the orbital speed for the ISS? Well, in the previous problem, we are just very quickly rearranged our centripetal acceleration equation for velocity, or excuse me, for speed, is equal to the square root of acceleration times radius. All right, so we are doing that here. So a couple things to note. So acceleration, we're given that. All right, so that is the acceleration, 8.78 meters per second squared. And then the second thing is the radius of the circular path. Right, so here, that's where we have to be careful. So it's going to be the radius of the Earth plus how high the ISS is above the Earth's surface. So our radius here is going to be 6,378 kilometers plus 360 kilometers. All right, so adding that together, naturally I don't have my calculator next to me. Did I write this in my notes for this example? I feel like I did somewhere. Oh, we'll skip it for now. We'll just write it like that. Okay, so to compute this then, so then our speed is going to be the square root of our 8.78 meters per second squared multiplied by the quantity 6,378, this is kilometers. Kilometers plus 360 kilometers. So something we're going to have to do is note we've got meters here and kilometers here. So we need to convert from kilometers to meters. So we can basically do that by multiplying by 10 to the third power, since there's 1,000 meters in a kilometer. So that'll convert then these to meters. All right. So doing this computation, we find out that the speed is 7.69 times 10 to the 3 meters per second. All right, and we could convert this to miles per hour if we'd like, just by doing some simple unit conversions, and we would get 1.72 times 10 to the 4 miles per hour. Right, so maybe that's easier for you to kind of think about in terms of speed. So the ISS is moving very quickly around the Earth. Right. So then based on that, so we're going to see what the how long in minutes the ISS takes to complete one orbit. All right, so this is actually a very interesting thing to think about. Let me move this upward. Fun fact, I can't really see my screen whatsoever. Okay. So looking at this, all right, solving for time. Well, we know the velocity, or excuse me, the speed, and we know that this is occurring, well, we know the definition of velocity, so the magnitude of which is going to be our speed, is going to be, well, we know speed is distance over time. All right, so this is useful because we want to find the time for one orbit. Well, one orbit is one complete circular path. All right, so this time, let's write it as capital T. Reason why I'm using a capital T rather than lowercase t is that you usually use that capital T to signify period, so the time it takes for one rotation, one circle. So looking at, since we're moving in a circle, well, one rotation, the distance traveled in that rotation is the circumference of that circle. Right? Well, we know the circumference of a circle, that's 2 pi r. Right? So this is going to be a very common equation that we'll have to kind of think about in physics. So this is not on your formula sheet, that the speed is 2 pi over t. That's something that that is expected that you will be able to think about logically and come up with this formula, right? That the speed is 2 pi r divided by t, right? It's the time for one circular path, right? So now it's just a matter of the radius. Again, our radius is those numbers added together, the radius of the Earth plus the height away from the surface of the Earth, the ISS is at. And we also know the speed. We just computed the speed the ISS is moving at. So 2 pi r divided by v will give us that time we're looking for. All right, so we're taking 2 pi, multiplying by the radius of our circular path. Oh, here's the number I was looking for earlier. Naturally, 6.738 times 10 to the 6 meters. All right, and then we divide by the speed of which it's moving. So this answer does depend on what we just computed. All right, so hopefully we did that correctly. If not, we can just always plug in the expression and go from there. Just making sure units work out. We've got meters, so we'll cancel with meters. So our final answer was going to be 1 divided by 1 over seconds, giving us just seconds. And so when we do this computation, we find that the period is 5.50, which then to convert that to minutes, which is what the problem asks for, we can divide by 60, since there's 60 seconds in 1 minute. Then we end up with about 91.7 minutes. So the ISS takes 91 minutes, so about an hour and a half, to make a full circular path around the Earth, which is pretty cool that we're able to compute that in kind of very straightforward math. All right, so hopefully that made sense. I have a couple of practice problems you're welcome to do on the back of this page that I handed out, this worksheet. All right, thanks for listening.